Hello everyone. This is Young Min from Yonsei University, South Korea. The talk for today is circuit interference cancellation circuit for automatic duplex system. So this is my outline. First thing is I will introduce automatic duplex system, which is in the event full duplex system, also include the sub-band full duplex system. Actually, that is discussed by the Communication System Society researcher. So I will introduce the advanced duplex system, and all those systems require self-interference cancellation. So I will introduce the microwave component circuit for the advanced duplex system. And as an example, I will introduce our effort from Yonsei University, phase array front end for FR2 advanced duplex, and small cell RF front end for FR1 advanced duplex systems. So we talked about this all the time. So event full duplex communication. So as we all know, we share the time and spectrum. So not like FDD or TDD, we share the frequency spectrum at the same time. So we can achieve twice more data rate. Since there is no guard band or guard ring, is going to be more than double the data rate. And because of we share the spectrum, we're going to have self-interference from transmit to receive, both in G node B and user equipment. But actually, we all try hard to cancel this self-interference, but there's still some problem, which is cross-link interference. We cannot cancel any interference from another user equipment. This can happen also in G node B, but UE are very close to each other. So there is no way to cancel this cross-link interference. Actually, that's the one reason we cannot deploy this full duplex system in 5G, even though it was talked about all the time. So people are talking about 6G, and they're trying to introduce this new duplex system in 6G communication. So they are talking about sub-band full duplex system. So in this case, G node B, the base station, do full duplex, but user equipment just do the time division duplex. So we need higher isolation and self-interference cancellation at G node B, but there is no self-interference cancellation required at user equipment. This sub-band full duplex system has been discussed in 3GPP as a study item and work item, and recently this figure was proposed in 3GPP region training. So this is sub-band full duplex system. The user equipment 1 and user equipment 2, they are all doing the time division duplex only, not the full duplex. But user equipment 2, if they require uplink, they start to uplink at the given frequency band. Generally, we use much more spectrum band for downlink and a little bit of uplink. But if there is some urgent request, we can do the uplink for user equipment 2. So we can support ultra reliable low latency communication using this sub-band full duplex. In base station side, base station always need to communication with user 1 and user 2 at the same time. So they do the uplink and downlink at the same time. That means the G node B need to do the full duplex. And it's going to be sub-band full duplex because they not share the spectrum. But in some case, we're going to use the automatic duplex system, not just FDD or TDD, and sub-band full duplex. At the end, they're trying to achieve event full duplex system. Then they call this as shared spectrum full duplex system. So automatic duplex system is not just in-band full duplex, they include sub-band full duplex and frequency division duplex, time division duplex, and all those things. One thing I want to say is, if user equipment 2 do the uplink, this will be the cross-link interference to the user equipment 1, but user equipment and 2 separate each other, and the frequency spectrum is not exactly the same. The interference is not going to be that much. So let's see the power spectrum at the genome B side. So in case we are transmitting 40 dBm at the transmitter at the base station, and our noise flow are going to be like minus 90 dBm. So we need to reduce this cycle interference to the noise flow level, and this transmit power due to the PA non-linearity, we're going to have ACLR around 30 dB lower, like the green line, and there will be also transmitter noise around here. For sub-band full duplex case, we need to reduce this power to the noise flow compared to in-band full duplex from here to the noise flow. So it's the required cancellation is a little bit relaxed, so it's a little bit easier compared to in-band full duplex cases. But still, there's no duplex filter or no guide band at all, so we still need to do some kind of set pre-interference cancellation. The required isolation going to be like 50 to 80 dB, depending on how much ADC dynamic range we're going to have. So generally, for the high output power from the base station, we need a lot of cancellation is still required. For the user equipment case for the spectrum, also we can consider this as a small cell RU radio unit cases. So our output power is only 20 dBm, the noise flow going to be same. So the required cancellation is relaxed. And another thing, for sub-band full duplex case, this spectrum, which is due to the PA etc., this power is from another different UV. So there's much of isolation between the UV are required, which is not that much. We may be able to do this much by pass loss between user equipment. So still, for this case, we have a little bit less power. Power, the required cancellation going to be around 6 dB, considering digital cancellation and ADC dynamic range. So this is the cancellation for the in-band full duplex or sub-band full duplex or automatic duplex system. We need the cancellation at the propagation domain antenna or circulator, and there is RF cancellation required, and some baseband circuit cancellation and digital cancellation can be possible. So in my research, we are interested in antenna propagation domain isolation and RF circuit interference cancellation. For the antenna isolation, so the left side is for the Juno B base station case, right side is maybe the small cell or UE cases. For 5G, we have like 32T, 32R maximum MIMO system, and people are talking about 128T, 128R extreme MIMO system. So we're going to have huge aperture for TX and RX. In this case, we can separate these two aperture to achieve the high isolation. We may be able to use the polarization difference between two aperture. So there is no the size limit for Juno B, so we can separate these two TXRX aperture and achieve the high antenna isolation, which is like 80 dB isolation. For small cell case or UE case, there is size limit. We cannot separate antenna, and there is not many antennas, so it's like 4x4 MIMO. So the antenna is not many, and we can use the circulator or this kind of system, and we need circuit interference cancellation circuit. And for another thing is RF circuit interference cancellation, so we need canceller. So if there is circuit interference between two antennas, we have a circuit to mimic this circuit interference using attenuator and phase shifter and delay element. And all this attenuator, phase shifter, delay element should be controllable to mimic the circuit interference. So attenuator can change the magnitude, but the phase should be the same at the same. The phase shifter have phase change, but magnitude level should be the same. And for group delay cases, magnitude is the same, but the delay is changing. So all this component is required to have RF circuit interference cancellation. And we can calculate this for the good high cancellation. All these components should have very good resolution to achieve high isolation. So this is the component that we have developed for this advanced duplex system. We did for FR1 and FR2 like gigahertz range and millimeter wave frequency. So this is some blocks that we have developed, and we're not going to have time for details every circuit, but I will put the note for the paper that introduced this circuit. This is variable attenuator at millimeter wave frequency. So this is distributed attenuator. We have varistor at 3 shunt cases, and by controlling this bias, we can have resistance change, and using some good matching and circuit component, we can have good magnitude variation. But the important thing here, as I said, when we change the magnitude, our phase should be stable and steady. So there's not much phase variation. If phase varies, then you have to recalibrate the whole tensor, so it's going to be too complicated. So this is phase shifter for FR gigahertz range. So for 5G, Korea is at 5.3 gigahertz. So we developed the circuit at 3.5 gigahertz range. So this is general ITPS phase shifter. By changing the load, we have input-output phase change. So this is how the load looks like. So another thing is, when we change this phase, we don't want much insertion loss variation. So this is just less than 1 dB variation over the frequency and over the phase state. And we have good phase resolution because this is analog phase shifter. And another thing is, there should be no delay variation over the bandwidth and over the phase state. So there's very low delay variation and insertion loss variation required for the phase shifter. This is the group delay controller. Actually, we need delay control. So best way, or maybe well-known way, is use two-time delay component. The two-time delay component have the immense amount of bandwidth, so it's hard to use. So better way is just control the group delay of the circuit. Then we're not going to have huge delay line. So group delay controller use reflection type phase shifter, but this is not the phase shifter. By using control the load. The load is based on resonator. When we change the resonant frequency, we're going to have different delay. So by changing this red load, you will see this red delay. But this bandwidth is very small, and delay is over the frequency. There's no center frequency. We have another delay element here. By adding these two together, so from port 1 to port 2, we experience two delay. So at the center frequency, we have flat delay. So by changing this load, we can achieve delay variation. And over the delay variation, we're not going to have much magnitude variation. So delay can be controlled by delay controller. Actually, there is no given well-known name for this group delay controller. We start to call this is GDC, but anyway, this is how we can change the delay. Another thing is on-chip circulator. This is well-known switch delay line circulator using CMOS. So there's two delay line on chip, which is designed by static delay line, and there's double throw switch and single port double switch. By on the switch, we can use this delay line or this delay line between TX and RX. We can achieve isolation and transmission. Isolation around minus 20 dB for these cases, and the power handling for P1 dB is around 5 dBm, which is not yet very high. So people are trying to use the gallium nitride or other high power transistor for higher on-chip power handling circulator. This is another on-chip circulator to achieve the isolation between TX and RX. This is based on distributed amplifier. Generally, distributed amplifier, if you have input here, your output going to have here, and you will achieve isolation at this point. In this case, we use 180 degree phase shift. By doing that, we can have TX and output is achieved at this port by having this phase shift, and there's another RX port here. The reason we using 180 phase shifter to flip the TX, RX and antenna output. By doing this, we can achieve wider isolation bandwidth, and even though we have a little bit narrower transmit bandwidth, so isolation is more important for augmented duplex cases. We use this kind of architecture to achieve isolation. So we can achieve isolation more than 20 dB. Actually, this isolation depends on how we can match antenna port, whether we are measuring or making system. So isolation is dependent on how we can measure this. So these were the component, not all, but most of our component that we developed. So as an example, we introduced phaser individual front end or FR2 or the band duplex system. So this is the cases. If our system is size of one TX and one RX, it's easy. Just putting one RF canceller, we cannot check good isolation. If it's minimum, like 4x4, then we can add N-scale canceller component. Then we can do the cancellation and isolation. But in case like phase theory or massive MIMO sub-array cases, we have huge aperture and TX and RX. We cannot have all this cancellation and secure cancellation for the antenna component. So what we can do is we're going to separate these two aperture, TX and RX, and do the cancellation at the common port. So our cancellation component can be decreased from N-squared to just single RF canceller. But we need to do a good isolation between the array or subarray. So this is a split system. We studied from the 8x8 phase array system developed by UCSD. So this is RX phase array, and this is TX phase array. For RX, we're going to use H port, and TX we're going to use V port. This is separated by 7 centimeter, and the gap between these two arrays is 3 centimeter. And this phase array system has single RF canceller. Actually, for this canceller, we use the beamformer. Every 4 antenna has single beamformer. That beamformer also use this for the canceller. We only use 2 channel for 2 channel self-interference cancellation. This is the system. To have high isolation between 2 TX and RX aperture, we separate these two. Not we just separate these two, we also use different pole or polarization of these two arrays. So when we scanning 2 arrays to the same direction, while we are scanning to the direction, our isolation can be achieved more than 40 dB. If we use same polarization, isolation is less than -30. By using cross polarization, we can achieve 10 dB, more than 10 dB more high isolation. And even though we have the common port isolation, we have to check whether all the received signal, received self-interference is low enough not to saturate the LNA element, because we don't have canceller for each antenna. We check all the input power at the RX array, so there is not much high self-interference at the antenna domain. So you can see a little bit higher power when your RX component, RX element is close to TX. And so there's TX and this is RX. So your power is getting smaller as you go to the far away from TX array. But this is depending on how we're going to be informing the TX array. So depending on the TX beam, we check all the LNA power. So we check there is no LNA saturation. And this is two-tap FI2 canceller. So as I said, we use the beamformer, and two channel has two different delay. And if you need phase shifter, you can use the beamformer phase shifter, and there is VJ for the beamformer. So by using beamformer, we can have the canceller. So by controlling the beamformer or canceller, we can achieve more isolation. With and without canceller, we can increase the isolation. So this is phase. The black line is the self-interference. By controlling the beamformer, we can make our self-interference beaming signal and self-interference going to be similar and with a 180-degree phase difference. This is the full system, and we could achieve 57 dB isolation between two TX and RX array at 28 kHz, and we could beamform any direction. And next thing is small staircase for iPhone 10, and for FR1 minor augmented credit system. So there is two antenna, and these two antenna are going to have these two antennas support 2x2 MIMO cases, and there is circulator for the single antenna for TX and RX, and there's another circulator for TX and RX. And between these two, there should be also another isolation. So we use decoupling network. So we call this is crosstalk, and for the circulator, we call this is self-talk. So for 2x2 MIMO, we need to have high self-talk and crosstalk isolation. For circulator, we need to have a good matching to have a high isolation. So there is reflection coefficient controller, so matching antenna impedance to the circulator to achieve high isolation here, and same for here. And between two antennas, we use decoupling network for high isolation. As I said, this is 2x2 MIMO. We need two scale, 4 canceller. So there is 4 canceller circuit. So our goal is to achieve 30 dB isolation from passive isolation and propagation domain, and there is 30 dB isolation, active cancellation. So this is the result. There is circulator and reflection coefficient controller and decoupling network between two antennas. So we can achieve 30 dB isolation from 3.6 to 3.8 kHz. So for the canceller, we have developed many different high-vol canceller at 2017, and we started from single tap attenuator, phase shifter, and group delay controller, but we could not achieve wide bandwidth. So we keep trying to have better way, multiple tap. For this demonstration, we use 3 tabs. So each tab has group delay, phase shifter, and attenuator. Because the group delay controller has limited delay variation, if we require, we can add additional fixed delay. So this is the case by developing this way. Compared to single tab, we can increase the bandwidth. So this is passive suppress SI by using 1 tab, 2 tab, 3 tab. So by increasing number of tabs, we can achieve better isolation, better cancellation. So as I said, if our target delay is here, if we don't have wideband group delay controller, we need a fixed delay. So adding fixed delay and wideband group delay controller together, we can achieve wider bandwidth. So this is first design, and we changed this group delay controller with fixed delay and group delay together. And the fixed delay filter looks like this. By using coupled line, input to output delay can be designed. So fixed delay is designed from 1 nanosecond to 7 nanosecond. Actually, there is not many delay filter that are available off the shelf. So we have to design a fixed delay. So by using this is how it looks like. There is tab 1, 2, 3, and this is 1 canceller. There is 4 canceller at this board, and front and back side. So this is antenna decoupling network and reflection coefficient controller, and this is controlled by AC at the bottom. So this is our small cell cases. This is final result from 3.26 to 3.8 for 200 mega bandwidth. We could achieve 55 dB isolation. By controlling our canceller only for 3.6 to 3.7, we can achieve better isolation, which is more than 60 dB. So depending on the target bandwidth, our isolation can be improved. So there is trade-off bandwidth and isolation. And I don't think there's enough time for this, but this is the recent work we are trying to do. When we're doing this, how we're going to control this, all the components, this is very important. Not just design is still hard, but design is just starting point. We have to know how we're going to control each tab. So there are so many degree of freedom. So we are trying to invent the best way to design this. So it depends on the sub-sampling. So we call this delay sampling, cancer architecture. So we are studying about how we optimize the cancer task. So this is the recent work. So this is conclusion. So advanced duplex system is discussed for 6G. G-Node B going to do the full duplex, but have duplex for user cases. There need array by array self-interference cancellation or between sub-array for extreme MIMO base station, and antenna by antenna self-interference cancellation for small cell MIMO radio unit. And we had developed phase shifter, attenuator, group delay for less variation, not to affect each other. And maybe we need fixed delay filter for low delay variation, and multi-tab canceller and systematic design is required. And that's it.
Cross-pole for your FR2 design, what is the link loss you expect by changing the polarization? So if you I think a TX was H pole or vice versa, B pole, and the other was the opposite. Yeah, this so you had it's like the left H TX. But the UE is gonna have, it's not gonna be perfectly aligned with those, right? So what do you estimate is the link loss, the polarization mismatch in the link?
It's going to be 3 dB, right? So
That's worst case, is 3
yes,
dB,
worst
right?
case. So it depends on the cases, but always if we use the polarization for our isolation, we lose the MIMO.
Right.
So that's good.
Yeah, okay, great talk, thank you.
So there should be better way not to use polarization, but it's not easy.
An additional question on this. Was this a single carrier over your complete bandwidth? I guess when you do this cancellation, you did it wideband.
Cancellation is done by wideband, so you can see.
But the maximum carrier bandwidth FR2 is 400 megahertz. Usually we have several carriers.
Yes, we can do
So
the
you need to do it
narrow bandwidth, but usually for RF we do the enough bandwidth and data cancellation going to be.
Yeah, but you need to do 3 or 4 in parallel. Because you want to remove interference from the first carrier, the second carrier, and the third carrier. But at the same time.
So, what? You mean we don't need?
No, because your system consists of several carriers, right? Over a complete bandwidth. And if you do subband full duplex, you only allocate a few PRBs per carrier in uplink. And there you want to cancel. And then you want to cancel another set of PRBs on the adjacent carrier.
Okay.
So will that, in your case, then you need several of these cancelers in parallel?
For yeah, data cancellation need to, you don't need to do, but data cancellation can do the specific band for RF cancellation.
Or can you have a frequency selective RF canceller that cancels only a part of the bandwidth?
So
Okay, may I?
I can discuss it later, yes.